How fast is he going down at the end?
Is it the same answer?
Rebecca, why?
I was thinking of that before they
Because
put 27.
he's getting to the same ground level.
Nothing in what we've done has changed. Now, the speeds are the same, the velocities are different, but the speeds are identical. And that's one of the powers of dealing with energy, is the fact that we do get the same answer for both problems.
You know what I was gonna say? No one ever got that, not, it wasn't no doubt, I didn't say it was snow down there. I thought you was gonna say it was that simple that no one really just got that it was that simple. No, like it probably is. She talked about
People do
snow.
think that it should be much more complicated than that, but if all we're looking for is speed, then it is as simple as that.
Yeah.
All right. Now, it turns out that there are stairs in the mountain here. And the kittens guide him, and he makes it back up to the top. While he's working his way up through the mountain, it snows again and fills in the gap.
The kitten's okay?
Oh, absolutely. Kittens are safely in the warm next to the fire. In the fireplace, it's not like the whole thing's burning down. I mean, watch out, you stick an infant on the slope, who knows what you do to kittens? Now, also, while it was snowing, the ski owner, because this is what ski owners do, put a giant spring down here at the end. It's a typical ski slip. Now, the spring here, we do need a piece of information. We do need that this is a lowercase k. This is known as the spring constant. We will get into spring constant in more detail in a later chapter, but for right now, the spring constant is basically a stiffness constant. It tells you how much force is required to stretch it a meter, or some unit of distance, usually a meter. So if this is 40 newtons per meter, that means it takes 40 newtons to stretch this spring or compress the spring 1 meter. It takes 80 newtons to stretch it 2 meters, or compress it 2 meters, 120 newtons to go 3 meters. I'm going to write that a little bit differently. 40 newtons per meter.
How'd you get that again?
I just give that number to you.
Oh.
The way that you would actually get it is, and I don't know if you will do this lab or not, but
You're talking about doing torque.
this would be chapter 12 or 13. You take a spring and you figure out what is the length of that spring right now, or you use this as a marker. And then you take a mass and attach it. And you see the length now. So how much it stretched from where it was to where it is now is basically the distance it stretched from whatever weight this is. So you do that weight divided by how far that stretched, and that's the spring constant. And the material, and if I put twice as much, assuming we don't deform the spring, if I put twice as much weight, it should stretch twice as far.
Is it tighter on your finger? Or are you using the force?
Oh, that?
Okay.
Yeah, there's a hook here so that you can actually hook it to something, or a loop here. But this gives you an idea of how much effort it takes to stretch the spring. Now, I do want to do one other thing, because now mass does matter. So if you would not come up with a number for mass earlier, you would need one now. I am going to give him more mass. Let's say that he did grow up feeding off of whatever food there was inside the mountains. He's an infant. It did take him a while to make it to the top, but he was fed, and so his mass will make him now 50 kilograms. So basically, my mass when I was in 8th grade. And the question is, how much will the spring compress? Because he's going to come all the way down, come ramming into it, it's going to shrink up, and at some point it's going to be at maximum compression. We now have two potential energies involved here. Because we have the weight that's still acting on them, but also we're gonna have spring, the elastic force down from the spring. So we'll have two potential energy formulas. And then you ask for spring initially.
That's it. Thank you.
G and S one.
What's the G for?
Pardon?
The G? What's the G?
Gravitational, there's the gravitational potential, and then there's the spring potential. We have two conservative forces, so we have two potential energy formulas. Sorry.
Okay, that's the spring final, the spring potential initial and then final.
Yes,
Okay.
absolutely. So that's MGH. This is 1/2 K delta X squared. Delta X is how much the spring is, in this case, compressed from its just natural state. I guess that's the initial. And then 1/2 MV final squared, MGH final, and 1/2 K delta X final squared. So what do we know? It's step by step. The initial kinetic energy is still zero, it still starts practically at rest. Initial potential, we have 50 times 9.8. What's the initial height?
100 meters.
And then 1/2 times 40, which is my value for K that I just gave you. And then what is so we have a spring just sitting there. How much is it compressed or stretched from its natural state?
And that is not compressed at all.
Therefore,
Is that 0?
and so my potential elastic is 0. And
Where do you get 40 from?
that value of K,
Oh.
that's
okay.
the spring constant, that's just how stiff it is.
Oh, okay. Let me just hold it on
I just gave that number to you. So this would be
49,000.
4,900?
Or
49,000.
1,000. So what is my initial total energy?
49,000.
All right. Now the finals. Can we eliminate, are any of these equal to 0, and then why?
Wait, what is final? Is it with this gear at the bottom and the spring compressed all the way?
Yeah, maximum compression, that's what final is.
Which one will be 0? Maybe the genetic final will be 0?
Why?
Because the initial was 0?
Ooh, not for that reason.
Oh.
Because the energy transferred.
Wait, yeah.
We started out with all this gravitational potential, it does transfer into other things. All right, so do we know, we have basically 3 variables here, VF, HF, and delta
Because
XF.
the initial is 0.
Say it again?
The initial is 0, the velocity.
It is, yeah, that initial, we already have 0 speed. On final now, so is anything equal to 0 at the end?
Probably not.
I think we're all stumped.
Oh, yes, somebody final, the potential energy,
We have two of them, so. The gravitational potential?
yeah, the final one. That one might be zero?
Why?
Well, that's what I was thinking, because the initial kinetic energy was zero.
Oh, that,
But you said no the last time, so.
The spring final. The spring final
the spring final,
will be zero.
why?
Because it's zero in the initial.
But the spring's gonna get compressed. It's gonna hit the spring's gonna compress. As soon as that spring starts compressing, delta X is not zero. That delta X is how far it is off of its natural state. So it will, delta X final is not zero. That's what we're actually trying to find. All right, so let's take it bit by bit. Final height, what's the final height? We established the initial height was 100 meters. What's the final height?
0 meters?
Yeah, that's zero. It's not because the kinetic is initially zero, it's because my final height is zero.
So what was that right, we just say know how to explain? Maybe you asked the question tricky, what did you ask us?
Do we know if any of these things are zero? And then you said final potential was, I assume you meant this one,
Yeah,
and I asked why. Sorry if that messed you up.
no, it shouldn't have, because that is the end of it down there. That's the end of
Bless
the
you.
line.
That is the end, and, all right, so we've gotten rid of one of those things. Either these other two equal to zero, and I just will tell you that yes, it is. One of the other two is equal to zero.
Kinetic final?
Why?
Because velocity is zero?
Why?
Because the spring is compressed until it can't compress anymore.
Exactly.
Big brain.
If he was still moving, that spring is still compressing or decompressing. It is, so maximum compression happens at that point when he stops. And so, all of my kinetic energy, well, what is my final total energy?
49,000.
And all of that comes from this spring potential. So 49,000, usually with only one 9 there, 49,000 is equal to 1/2 times 40 times delta X final squared. So now, it's a similar type math problem to what we've already done. We have 49,000 equals 20 times delta X. I'm just gonna simplify my notation here. Instead of writing all that out, I'm just gonna use X squared. Divide by 20. So I get X squared is equal to 2450.
Yes.
Yeah, one more zero. Oh, I did two, never mind.
You should get 49.5
49.5 what?
meters per second.
What do we actually find?
It'd just be joules, wouldn't it? The potential?
I was saying, we found the spring potential.
Well, the spring potential is 49,000 joules. But we have this 49.5 here.
Is it the newtons per meter?
Physically, what did we find? Don't worry about the number right now. What were we trying to find?
That's a good question.
The energy of the spring.
That was an intermediate step. What was the final step?
The final. I don't know.
How fast we go? No, sorry.
Did I write it down somewhere? That would be nice if I actually did. No, I just spoke it. I wanted to know how far the spring compressed.
Oh,
So what are the units?
Newtons per meter.
SI? Well, no. Well, they don't have no,
centimeters?
What was that?
Centimeters? Or meters?
It would be meters. I think where centimeters would come from. Did you multiply by 100 also? It's meters. That's how far the spring compressed.
okay, so we will be using, and that's the formula that we will be using right there, the 1/2 times 40?
Yeah, the 1/2 K, since all the energy is in the spring at this point, potential in the spring,
1/2 K,
times how much it compressed squared.
okay.
It looked like you were about to ask a follow-up question. Okay.
Probably, where you get the 20 from? Oh, that's divided into 2 and 40. No,
Yeah,
where's,
so the 1/2 40 is 20, so,
oh,
sorry, 49,020x squared divided by 20.
I didn't do the math, sorry.
Okay. All right, a couple of follow-up questions here.
Never mind.
I'm gonna put it down, that's what you did.
All right. So we'll take a look at the energy bar graph. There's an official name for it, I forget what it is. So we start out with all this gravitational potential. And we have no kinetic, and we have no elastic potential, or spring potential. So it starts out all gravitational potential. When he gets to here, he's moved down, so he's lost some potential, lost some gravitational potential in here and made more kinetic. So at this point, that's roughly halfway between. So make that roughly half the size. So it's u sub g, kinetic. And then still, the elastic potential hasn't changed, nothing's doing anything to the spring. When he gets to here, he's gained some potential and he's lost kinetic. He slows down as he goes up the hill. So the potential would be a little bit bigger than it was. Kinetic, he's lost some, and the elastic potential, still nothing. When he gets down to here, it's all kinetic. So at this point right here, his gravitational potential is 0, because we said so. Our spring potential is 0, because we haven't hit the spring yet, and it's all kinetic. And then it hits the spring, he starts losing kinetic. Gravitational potential doesn't change, it's still at 0. And so by the time we get to maximum compression, at more than the half length of a football field, UG is 0, K is 0, and it's all spring potential. So the amount of gravitational potential depends upon the height, the amount of elastic potential or spring potential depends upon how much it's been compressed or stretched. Questions to hear? Now I see what I've forgotten to tell you. Definitely done that, definitely done that, definitely done that. Oh, power. For some reason, I just don't like power.
Have a good day. Have a good day.
Zoe, hopefully I'll see I saw the email before, but hopefully I'll remember to scan your test and send it to you. So if you don't get it by tomorrow, send me an email, and just ask for the scan, please.
Okay, thank you.
Thank you.
Bye-bye. Have a great day.
You too.
Thanks.
And now place your bets where the top of her head shows up in the video. So something that they did not see, and so hopefully I'll remember when I see an email or when I send the scan to also post that when the quiz is gonna be. 6 and 7. We've done 6 and 7, but we haven't had a quiz yet. And I feel like part of you is dying inside because we haven't done that yet.
If, we really are.
No. No, we're not. No.
So today's the 19th.
Oh,
of the fall break.
Happy with you take the quiz on 12?
You wanna take the quiz on October 12th?
Uh-huh.
The time machine's broken. It's really messing me up. The joy of having meeting only one day a week. So 2 chapters. You've done it before, 4 and 5. Same drills before, under the coursework, chapter 6, there's the set of problems posted, and for chapter 7 also.
Quizzes.
Quiz
Talking
on
about
6
the
and
chug
7.
Like the chug and plug joint you doing.
Yeah, there's one of each type. So I think there's one plug and chug, one think and explain, one think and discuss, and whatever the others are.
Nice job. Now, the last time I was looking at what you told me to look at, mister, and you know what, I think, I'll talk to you tomorrow.
All right. Any questions before we double the number of formulas we've dealt with? Oh yeah, that's a look of excitement. All right, let's do it, let's double.